To start our day, our first session is about transcritical CO2 refrigeration. It's a natural refrigerant solution that's gaining momentum across the industry, as many of you will know. These advanced systems rely on smart controls and real-time data to stay efficient and reliable. Please welcome Ryan McAndrews, Manager of Controls and Energy Solutions at Copeland, to share how modern control technologies are helping CO2 systems succeed. Thanks, Ryan. Do you want to use that, or do you want to get a...
I'm fine with this.
Yeah?
Is there
He's got that one right there if you want.
No, that's fine. We'll do this.
Leave you to it.
Good afternoon, everybody. Welcome to the ORAC Fall Forum. My name's Ryan McAndrews. This is my first ORAC Fall Forum, so I'm glad to be here. A little bit about myself. I've been in this industry for about 20 years now. I started off as a first-year apprentice, getting into large HVAC systems. Came across an opportunity to get into supermarket service and figured, why not? People need to eat and get groceries. So there's always going to be something to do there. A couple years doing that, I came across, I took advantage of doing preventative maintenances and figured, why not? Let's dive a little deeper into some refrigeration systems. And that got me into the weeds on how refrigeration racks work. Got me looking into the trends and the peaks and valleys, and I always had a goal on trying to make them better. So I got pretty good at that, and then I got an opportunity to get into starting up some new refrigeration equipment. That was a blast. Fast forward a couple years, I got back into HVAC commercial controls, Lyric Land. Did that for a while and came across another opportunity to work for Copeland. So over at Copeland, I wear a few hats. I manage Canadian field service. I support our sales team, support OEMs. I support the larger retailers in Canada, and I dabble with some training here and there. So today, just going to kind of talk about kind of like an intro to CO2 controls. It's not going to be an engineering deep dive, more on fundamentals and some basic principles or some main components, because to get into the weeds, it'd take a lot more than 40 minutes. I guess before we start, can I get a show of hands on who works on CO2 equipment? Niche. So I'm just going to go over some basic rack operation stuff. Gas coolers, some valves, case controllers, or evaporator controllers. I guess before we get into that, CO2 transcritical booster. That's a bit of a mouthful on what you would call it. So transcritical, just to touch on that, we get our pressure enthalpy hats on. When we exceed an ambient of 87.8 degrees Fahrenheit, we no longer have a relation of temperature and pressure, so we're in a bit of an unknown. So that's going to be the transcritical point or the supercritical point. So that's why we no longer call it a condenser, because we're not condensing anymore. We're just de-superheating. So we call it a gas cooler in its place. Regarding the booster, typically, like in the diagram that's on the screen, it's a typical diagram of a booster. The booster portion is the low temp compressors that are boosting pressure up to the medium temp compressors. A lot of words thrown on the screen, but we're just going to talk about it. So typically in a rack, hopefully you're a manufacturer, you're going to have two groups, low temp and medium temp, and the example I'm using would be like a grocery store application. Medium temp being fresh food, meats, produce, etc. Low temp being various frozen foods. In the groups, you'll have various capacity control being typically, now we're seeing a lot of frequency drives, which in the HVAC field, obviously VFDs have been around for a long time, being in chillers, air handlers, and all that stuff. But getting into racks wasn't entirely that common up until the last maybe 5 to 10 years. So being that a typical rack will have various stages of compressors, they'll have some modulating compressors, and same with the low temp, you'll also have some modulating compressors as well. These racks, you can have some that are just medium temp or just low temp. However, if you have low temp, there needs to be some consideration on having the low temp boost up to the medium. Saying that, with the low temp compressors, they will not run if the medium temp compressors are in a failure state. So there'll be various rack controllers. There are many brands out there that do it, ours included. There'll be interlocks for looking after medium temp compressors, various fail states, phase loss, et cetera, et cetera. Touching on variable speed, there's more and more technologies coming out from the OEMs where you'll find even multiple variable capacity compressors on each suction groups. Various other methods of capacity control. There's typically another suction group you can call being parallel compression, which the name can be a little confusing because technically on a rack all the compressors are piped in parallel. But parallel compression, not as common in a grocery store state. It's usually on the large machines, cold rooms, et cetera, et cetera. For the medium temp compressors, we have to look after superheat. As HVAC mechanics, refrigeration mechanics, we all know superheat, how important it is. So it is critical on these machines to maintain superheat. So in a medium temp suction group, we like to maintain anywhere from 20 to 45-ish degrees Fahrenheit superheat. So to accommodate for that, we're kind of bringing back some old technologies, being it's some liquid injection or demand cooling, or even some hot gas injection to maintain various superheat levels. If you have an application where you're more focused on low temp, you'll have to take some consideration and significant amount of demand cooling or liquid injection for that medium temp suction group, hence all of the low temp load that's going into it. Same can be said if you have fairly low load on the low temp or medium temp. You may need some hot gas to make sure the superheat levels are adequate. CO2 low temp superheats, they're higher than what most compressors are accustomed to. I know we like to say 36 degrees minimum is what we like to see on our low temp CO2 compressors. I want to say the other manufacturers are, if they're not the same value, they're very, very close. Hot gas, just touching on that again. It's just to maintain superheat levels in medium temp. Let's jump into oil. Oil is probably the voodoo of our CO2 systems. There's a lot of testing going around various manufacturers, changing temperature of oils. It's probably the biggest nuisance in a CO2 system. There's a lot of critical points to it because whenever CO2 system gets installed, obviously every contractor is purging with nitrogen every single time they're doing brazing, but it's critical for the amount of debris, soot, whatever it may be, oxidization into the pipes, because the filters are really fine, and dirty oil can be your enemy in these systems. Typically, you'll have on your medium temp compressor, your low temp is discharging into medium temp. Medium temp is going into a typical oil separator, coalescing or centrifugal, whatever it may be. And then it collects typically in a external oil reservoir. Nothing too crazy from there. The reservoir then feeds oil to your compressors. Your compressors will have an electronic oil regulator mounted onto the side of them. Typically, we like to see an oil differential between the oil reservoir and the crankcase of the compressors, magic number around 75 psi. Any less than that, you're going to start to get some headaches with oil. you won't be able to fill the compressor crankcases in time. The rack controllers are going to have a tremendous amount of sensors on everything because, again, oil is quite critical, same with any other large HVAC machine. We're monitoring oil temperature, oil levels, oil flow, and if we ever get into a state where low oil condition, the rack would go into a fail state. We'll touch more on a fail state shortly. Gas cooler, again, this is also known as the condenser. So if we're in our transcritical state, we're not condensing, we're just desuperheating. Gas cooler control is quite critical. Typically, we look to maintain a TD of around 5 to 10 degrees Fahrenheit. We're looking at the gas cooler outlet temperature. Well, there's quite a few strategies. Looking at the outlet temperature of the gas cooler and then the ambient to get the TD. In our ambient, we seem to be getting away of not requiring any kind of water or adiabatic cooling into it. A dry gas cooler seems to be sufficient in our ambience today. Where that is in 10 years from now, probably not. Something to consider for controlling the fans. We like to take into consideration a failure state. So from a control signal perspective, it is a good habit to, instead of sending out a 0 to 10 volt signal, we like to do 10 to 0. So in a failure state, our fans fail full speed. HPV, BGV, so high pressure valve and bypass valve. So the HPV kind of has a bit of a slang term of being called a magic valve, which is kind of nonsense. It just makes it scarier than what it seems like. You call it a magic valve, people are just kind of not knowing what it does if you call it a magic valve. Essentially, all it's looking to do a couple things, depending on what the state of your machine's in. So this is going to be on the outlet of the gas cooler, and its primary task, it's going to be holding refrigerant in the gas cooler or condenser if it's subcritical at this point. It's maintaining a minimum pressure. Once you maintain your minimum pressure and you're full in operation, you're simply maintaining a subcooling level. If you're in a high ambient state, transitioning, you'll have to transition up from one mode to another, and it's trying to maintain, for the most part, a simulated trend of the PT, of the pressure and temperature on a CO2 scale. So we're making some assumptions past the critical point. Otherwise, it's just maintaining flow going into the tank. Something to take into consideration is whenever there is going to be a failure state, let's say a power failure, there needs to be some consideration on where the valves are sitting, where do they reset to, because being that CO2, and again, it's the transcritical pressures can run quite high, potentially run at around 1500 psi, which requires some other details on how the piping works. In Canada, we have to use stainless steel piping. We can't get away with copper on the high side. In the US, they can use XRP and whatnot. In Canada, it's not good yet. So whenever there's a failure state, we have to consider reliefs. Which reliefs, what do they blow at? Where does the gas go in a failure state? You want it to fail up to the high side. Bypass valve. This valve is going to be on an outlet of the flash tank or the receiver. So it's pretty easy job on what this one's doing. It's just looking to maintain a pressure in the tank. The interesting thing with that is what's maintaining the liquid temperature of the refrigerant. So being if you have a design temperature of liquid of 35 degrees, your pressure set point of your tank is going to be the equivalent of 35 degrees. So if you can't control your flash tank, if your valve peaks and valleys, it's not working, it's going to snowball into the entire system. So this valve then, it allows gas flow from the tank to your medium temp compressors. If your valve is hunting, your compressors are going to hunt, then your gas cooler is going to hunt, then your high pressure valve is going to hunt, and then it just continues to snowball, which most likely it'll crash shortly afterwards. So it's tuning the peaks and valleys again is quite important. Case controllers or evaporator controllers. Yeah, CO2 electronic expansion valves on everything. Being if they're stepper valves, pulse width valves, we need electronic control on all of them. Primary reason is for the sake of a shutdown scenario. We want to be able to disable the circuits if in a shutdown scenario or state. Aside from that, the case controllers or evaporator controllers are maintaining efficiency of the evaporator, being controlling the fans if they're variable speed, or controlling superheat levels, resetting superheat levels, looking after lights, heaters, hot gas valves, all the above. Otherwise, also the evaporator controllers, if you get into some more elaborate control in your systems, you can get into demand response events. So in a demand response event for whatever utility service it may be, you could offset defrost times, offset superheat levels and whatnot to capitalize on a kilowatt hour reduction. Shutdowns and startups. This is probably a stressful point for a lot of folks working on these systems, is when you turn them on for the first time. A lot of technicians out there are just concerned on the pressures is probably their big stress point. So starting up a system, you need to make sure obviously there's enough refrigerant into the system. Get a medium temp compressors is what gets fired up first, and then you slowly bring on your evaporators. Your rack controller should be sophisticated enough to stage the loads, the evaporator loads when it turns on. Turning them all on in one shot may overload the suction group. Pressures get high, you may have a high pressure event. In the event of a high pressure scenario, there's to be various interlocks into the system, being low temp, again, as I mentioned earlier, low temp is tied into medium temp. Low temp will not function if medium temp is functioning. The case controllers or evaporator controls will have to get shut down. There's a various sequence on how it gets shut down, and then when it gets back started again, same idea. You stage everything back on. Also, in the event of a prolonged outage, quite often these systems have a type of auxiliary unit where the CO2 in the vessel will be refrigerated from another system, a small little condensing unit, whatever it may be, to keep the pressures down. Worst case scenario, the release pop, and then you lose hundreds of pounds of refrigerant, and most likely the grocery store is going to be calling a reefer truck, and that's where all the food's going to go. So these auxiliary systems are intended to keep the pressures down while there is an outage or scheduled downtime or whatever it may be. Some manufacturers getting a little creative. Instead of using another refrigerant or 448, whatever it may be, they're using the CO2 of the system itself. So it's a better idea using the refrigerant of the system that's there. Some larger systems, typically they'll have battery packs where the auxiliaries will run for several hours. Previously, there were even some machines that would have natural gas generators, which makes you scratch your head on you have a natural refrigerant system being kept alive by a natural gas generator. CO2 systems have a tremendous amount of data, being all the evaporator controllers, everything with the gas cooler, tremendous amount of points of data over at the racks themselves. Saying that allows you, with that data, gives you more opportunity to fine-tune various components of the system. I stress the importance of, prior to starting a CO2 system, all the I/O, the inputs, outputs, everything needs to be validated. A tremendous amount of importance on that. And ideally, you get suction pressures optimized from there, gas coolers optimized, your valves optimized, and you continue to go. There's a tremendous amount of data available. lots of opportunity to optimize them. It just, unfortunately, usually there's a lot of corners that are cut. So it's just, I stress the importance of taking your time, optimize, use the trends. Trends are tools. Peaks and valleys, flatline them. Yeah, it's CO2 is it's here to stay. It's not going anywhere, and that's it.
Before I give the microphone back, there might be some questions. I have one. Are we likely to see CO2 in more conventional equipment such as rooftop units and comfort cooling split systems?
There are some manufacturers that are working on CO2 for, I think the air handler is around 20 tons and greater. There's quite a few manufacturers looking into that. Smaller systems probably not, because I don't think the compressor technology is there. Same with non-racks or non-parallel systems. You'll start to see them in condensing units in the very near future too.
Any other questions? I've got a microphone here I can pass on to some people, right? You're supposed to know all this stuff already.
Hey Ryan, you touched on the high side being stainless steel only in Canada. Do you know if Canada will ever introduce the copper side?
I don't have an answer to that. That's a question that a lot of contractors and retailers inquire about quite often, because there's a bit of a resource constraint on having the welders available. I think every contractor that deals with CO2 has that limit. As far as I know, hearing from TSSA and whatnot, it's not changing anytime soon. So we'll hope with success out of XRP and whatnot, other copper in the US, that maybe it'll come back up here. As far as I know, if you have a packaged unit from a manufacturer where there's no remote field piping, then it's fine. But if it's field piping, you require the stainless.
Thanks.
I know nothing about CO2 refrigeration, but I had a call the other day from someone looking for a brazing procedure to join stainless steel with copper, because there's copper apparently on the rack system, and if you want to connect your stainless steel pipe to it, you need a special welding procedure. We got past that, but I'm wondering how are they allowed to use copper on the rack systems if they can't use it in the piping?
The copper on the rack from the manufacturers will be the iron embedded copper, being the XRP. Regarding that procedure that you were talking about, that has been a headache in various provinces. I think New Brunswick has actually been the biggest headache for that. They usually they want an engineered procedure from the manufacturer. How do we do this? Unfortunately, the manufacturer is usually not providing documentation that's meets their needs, so it's usually a bit of a painful process. But from what I understand, I think most of the provinces or the boiler inspection agencies, they've crossed that bridge and finally sorted it out. But yeah, it definitely was a headache.
Well, for a small fee, I have the name of a welding engineer who can fix you up.
Perfect.
As a small token of our appreciation for your time today.
Thank you very much. Thank you.
Thank you.